तो होगा, but let's say in the beginning ये वाला बेहतर। जी जी। Okay, so let's begin. आज जो है आई थिंक इट्स वन ऑफ द क्रिटिकल लेक्चर्स इन दिस कोर्स, क्योंकि आज हम जो है इफ यू आस्क मी वी बिगिन द कोर्स realistically today. I mean, in terms of physics that we are going to discuss in the rest of the course. अब तक जो हमने चीजें की हैं, if I summarize them, we essentially try to understand the basic axioms of quantum mechanics for closed quantum systems, and then we also learned the mathematical structures, especially density matrix formalism, to deal with the open quantum system, but we did not specifically dealt with any open quantum system so far. But today we begin the discussion and understanding of how to model open quantum system, और ये जो बाकी सारा course है, it's mostly going to be along these lines. So what we will do that in the next few weeks we will develop the density matrix formalism further to see how we can sort of understand the dynamical evolution of open quantum systems. And then my focus is actually going to be with respect to quantum computing. So I will be thinking in terms of these issues कि अगर हमारे पास एक quantum computer है which is essentially a set of qubits which with the possibility of controlled unitary operations. So we know that we can do a lot of things efficiently, more efficiently on a quantum computer than a classical computer, even though we didn't discuss it in this course, but that's something separate. But the actual quantum computers हैं, they are noisy, and as they should be. We will see that it's very hard to have a quantum system which is not noisy, and hopefully during this course we will also understand why we can't have at least a noiseless quantum computer. So noise is essentially the integral part of quantum computer. And जो examples हैं उनमें I'll be thinking about errors that are incurred in quantum computer due to noise, and how to model those erroneous evolution of our qubits. Plus we will also spend some time on error correcting codes then using this same formalism, and hopefully we will still have some time to study quantum information theory, which is more relevant for communication protocols as well. But कोशिश ये होगी कि we go now slow and thoroughly, ताकि जो at least जो एक चीज है जो quantum computing में जो noise processes हैं उनकी modeling जो है वो हमें आ जाए. Okay, so let me begin by discussing noise, quantum noise, and also we will introduce today a formalism, one of the formalism for what we call quantum operations. By the way, इससे पहले जो है वो हमने जो नाइल्सन चुआंग है उसका चैप्टर 2 जो है वो ऑलमोस्ट कंप्लीटली जो है वो फॉलो किया है, और उसके साथ हमने कुछ टॉपिक्स चैप्टर 4 से किए हैं, एंड देन लिटिल बिट्स फ्रॉम हियर एंड देयर. फॉर एग्जांपल जो डेरिवेशन थी बैलेंस इनइक्वालिटी की, दैट केम फ्रॉम बुक बाय बार्नेट, और इसी तरह दरमियान में डिस्कशन जो है वो इधर से है. बट इफ यू कैन जस्ट फोकस on chapter 2 and initial topics of chapter 4 where we have single and qubit gate and multi-qubit gate, that's going to be enough as we go forward. अलबत्ता अब से आगे जो है we are going to start from chapter 9, and I'll try to go almost linearly from now on. So for reading purposes, और आप अगर देखना चाहते हैं कि आगे हम क्या करने जा रहे हैं, so you can keep reading it. कहीं कहीं पे I'll be skipping a few things which might be tangential, so that we can cover more concepts as we go on. Okay, so logistics aside, so let's start from a discussion of closed and open quantum system. So a closed, actually I will just use the word system because everything is quantum, so I don't have to qualify with quantum. So a closed system doesn't exist in the universe, really speaking, except if you think of the universe as a whole as a system. Because other than that, everything that we work with, we look at, we observe, we try to do anything, it's just part of the universe. You can isolate it as much as you can, but you can never make the interactions between the system that you are studying and the remainder of the universe to zero. So a closed system is an approximation. It doesn't exist. So therefore, what we have to do is always work with open system. Now, uh, it does turn out actually most of the progress in sciences, especially in physics, has actually taken place because people were able to imagine closed system. They were able to, neglect interactions so that sort of try to come at the laws. For example, the Newton laws, you can reach those conclusion only if you sort of are able to zoom in on a single particle and nothing else in the universe, and maybe a mechanism to act a force on it or so on. Similarly, the relativistic equations all most of the things are developed for closed quantum system. But of course, there are ways to study realistic system as well. Just to give you an example, क्लोज और ओपन जो सिस्टम है वो कैसे रिलेट करते हैं. फॉर एग्जांपल, इफ वी लुक एट अ पेंडुलम, so a pendulum is a very messy thing if you really look at it. For example, it has a string which may not be very straight, exactly straight, might be a little bit doing like this, but if you have a pretty good string, you can think of it as a straight line. This ball of mass, it might not be exactly uniform inside it. It might not be point, but by imagining it to be a uniform distribution, you can think of it as a point mass. And even you can think of this chord to be massless, and then this you have tied it with something over here. So if you, and then you can imagine that it's going it's oscillating in a vacuum. So you can neglect its interaction with air. And since most of the time we are doing this experiment on Earth, and you can then imagine that Earth is not spherical, so that its gravitational pull on this ball doesn't change when this ball goes from here to here, and so on. So after making a lot of these assumptions that gravitational pull here and here and here, it's the same, we can sort of think of it as a closed system which is just oscillating. Once it starts, it can keep going. So by making a lot of these approximations, we can think of this open system as a closed system. And then when we imagine it as a closed system, there are many nice things that we can compute for this system. For example, for this pendulum, you can talk about what we call natural oscillation frequency, right? In other words, the period. And you can come up with laws. Okay, the period is related to the length of the pendulum and so on. And you can talk about the impact of this gravitational pull on the period. So if the pendulum is here, or it might be somewhere else where G is different. But of course, again, if G different over somewhere else, but same during this motion. So we can think about the dependence of period on this gravitational pull and so on. So there are many things that we can talk about it. But this has one important property, and that is that once this is set into motion, it keeps on going forever. That's the property of this closed quantum system. लेकिन कौन सी बात? हाँ मतलब कि अब ये जो पेंडुलम है, इट्स अ क्लोज सिस्टम. इफ यू निग्लेक्ट एवरीथिंग that is disturbing or giving it noise, then this is a closed system, right? और अगर आप इसको एक दफा ऑसिलेट कर दें तो then kinetic energy converts to potential to kinetic, and it keeps going. There's no friction, there's no dissipation that's taking place. So it's not real in the sense that we don't see this thing anywhere in the world. But this idealization is important for many things. This helps us understand what's going on. So, but there are many things that we can do if we just keep it imagining as a closed system. For example, अगर आपने clock बनाना है, ठीक है? तो clock के लिए you need something that keeps on oscillating. अब उसके लिए आपको फिर ये पता होना चाहिए कि ये फ्रिक्शनल फोर्सेस कितनी है, कितनी फोर्स में इसको पीरियोडिकली लगा, कोई मोटर लगाई हुई है या कोई मैकेनिज्म है स्प्रिंग्स और पुलिस का, which give it a push every time it goes like this. Then you have to start thinking about its interaction with its environment. So there are many things that if we want to do that, we have to model this system as more realistically than as an open system. For example, if you want to find out, why it stops. क्योंकि अगर आप एक रियल पेंडुलम में इसको ये छोड़ दें, थोड़ी देर के बाद वो ज़रा रुक जाएगा. So for this, you have to model the interaction of this pendulum with its environment. Or for example, how long does it keep going? For example, it's you can say it's decay time. कि अगर ये इसका plot करें, so after a while, it decays. So if you want to characterize के ये अगर इस तरह से decay कर रहा है इसका amplitude, so what's this constant? So similarly, there are many other things. For example, if you want to ask, okay, what if I want to keep it like this? What I have to do, and so on. So जो जितने भी practical questions हैं, for them to answer, you have to model it as interacting with an environment. So you have to model it as an open system. अब ये जो second part है ना, open system modeling, this is not straightforward. And it takes little bit, getting used to of thinking of ways that you can model it, better. For example, जो एक I would say one physicist, can start thinking about modeling. बल्कि चले, let me ask you people. क्यों बात अगर आपने pendulum की interaction model करनी हो environment के साथ, so what should be done? I mean, how you should think about it? कोई तरीका बताएं. You want to understand why a pendulum, stops after a while. नहीं, अब आपको देखना होगा कि एयर रेजिस्टेंस क्या चीज है, एयर रेजिस्टेंस कहां से आ रही है. ओके, गुड. एंड देन ग्रेविटेशन पुल तो नहीं रोकती उसको, बाय द वे. क्यों? आप जब पेंडुलम को क्लोज सिस्टम के तौर पे मॉडल करते हैं, उसमें ग्रेविटेशन फोर्स होती है, बट वो तो उसको कभी स्टॉप नहीं करती. वो तो जब इधर होता है तो उसको इधर धक्का देती है, जब इधर होता है इधर धक्का, तो वो चलता रहता है. अब फर्ज करें कि आपने, लेट्स फॉरगेट व्हाट्स हैपनिंग ओवर हियर. अगर आप एयर के साथ इसकी इंटरेक्शन स्टडी करना चाहते हैं, सो रेजिस्टेंस का वर्ड जो है ना वो हम एक यूज कर रहे हैं. सो हाउ टू फाइंड आउट कि कितनी ये रेजिस्टेंस है? आर यू गोइंग टू देन स्टार्ट मॉडलिंग के मेरे पास एक ये पेंडुलम का स्फीयर है और इर्द गिर्द एटम्स जो एयर है उसके पार्टिकल्स हैं, वो उसको डिफरेंट तरह से बाउंस कर रहे हैं. when it's going like this, some balls are hitting from this side, some are hitting from this side. Yeah, you want to model air as a fluid and then bring in fluid mechanics concept and so on. So there are many ways to do it. लेकिन दूसरी जो इंपॉर्टेंट चीज है कि अब ये जो बिजनेस है ओपन सिस्टम का, इट्स अ मैसी बिजनेस। क्यों? क्योंकि बहुत सारी चीजें हैं जो इसको इफेक्ट कर रही हैं। फॉर एग्जाम्पल, अर्थ जो है वो स्फेरिकल है, तो हम इसकी मॉडलिंग में अक्सर ये ऑप्शन करते हैं कि जो जी की वैल्यू यहाँ और यहाँ सेम है, यानी ये हाइट ये है, यहाँ पे सेम, तकरीबन हाइट ज्यादा डिफरेंस नहीं, हम सेम मान लेते हैं। अब हमने ये भी सोचना है कि क्या हम जो जी की वेरिएशन उसको भी लेके आए यहाँ पे कि ना लेके आए, एंड सो ऑन। और ये जो बॉल है इसकी अपनी जो डेंसिटी है वो भी यूनिफॉर्म नहीं हो सकती, दैट आल्सो इम्पैक्ट थिंग्स, एंड सो ऑन। सो जो इन्वायरमेंट है उसका जब इम्पैक्ट किसी सिस्टम पे हो रहा होता है तो यूजुअली इट्स वेरी कॉम्प्लिकेटेड। अब उसमें दो एक्सट्रीम जो है ना वो आप कर सकते हैं, अपने जहन में ला सकते हैं। सो वन एक्सट्रीम इज यू निग्लेक्ट environment completely, and that is the closed system idealization. The other is you include everything from the system, from the environment. अगर आप environment से हर चीज शामिल कर लेते हैं and you set up lot of equations together with all the variables in it, then of course you can put that model into a computer, और कंप्यूटर के अंदर चीजें स्पेसिफाई करें, जो एयर है उसके कंपोजिशन स्पेसिफाई करें, ये भी कंसिडर कर लें कि हाइड्रोजन गैस है इतनी है, नाइट्रोजन इतनी है, फिर नाइट्रोजन के आइसोटोप्स भी होते हैं। एवरी सिंगल डिटेल दैट यू कैन थिंक ऑफ यू कैन पुट इनटू द मॉडल। उससे क्या होगा, यू कैन ऑलमोस्ट एग्जैक्टली प्रिडिक्ट, okay, let's forget about the quantum uncertainty, but keeping into the classical world, if I can specify the environment exactly, I can exactly predict कि ये जो पेंडुलम है वो किस तरह से जो है वो बिहेव करेगा, इसमें वॉबलिंग कितनी होगी, ये कितने टर्न के बाद स्टॉप कर देगा, एंड सो ऑन। लेकिन प्राइस का पे की है, प्राइस हमने ये पे की है कि हमने अपना मॉडल ही बड़ा कॉम्प्लिकेटेड बना लिया। ठीक है, कोई बात नहीं, आप यू कैन थिंक ऑफ अ कंप्यूटर, लेकिन जो उसका नुकसान हुआ है ना, एज ए फिजिसिस्ट आई इफ आई वुड थिंक आई विल लूज ऑल इनसाइट। जब भी आपकी मॉडल बनाते हैं ना, जब उसमें नंबर ऑफ पैरामीटर्स बढ़ते जाते हैं, सिस्टम की कॉम्प्लेक्सिटी बढ़ती जाती है, तो उसकी जो प्रिडिक्टिव पावर है ना वो बढ़ती जाती है। आप उस प्रॉब्लम को सॉल्व करके तो जो फ्यूचर कोर्स ऑफ एक्शन है वो प्रिडिक्ट कर सकते हैं मोर एंड मोर एक्यूरेटली, बट यू स्टार्ट लूजिंग इंट्यूशन। अब एक सिस्टम है उसके अंदर 50 वेरिएबल है, अब मेरा जहन जो है ना वो तो कभी भी कैन गेट अराउंड दीज 50 वेरिएबल। यूजुअली फिजिसिस्ट, if there is more than one variable they just lose it, they can, and that it's almost human like thing, okay? You can easily understand the impact of one variable and things that you can explain. दो हो जाए तो you start doing the gymnastics like this, and then after two almost it's done. You say okay, you solve this equation, यहाँ से ये आता है, and it becomes harder to come up with an intuitive picture. और इंट्यूशन हम चाहते क्यों है, पहला ये भी सवाल है, बस हमें इंट्यूशन क्यों चाहिए होता है? चल अली सादन से पूछते हैं, क्यों अली? जब हम एक प्रॉब्लम सॉल्व कर रहे हैं, लेट्स से कि ये पेंडुलम ही जैसे है कि इसके एनवायरनमेंट के साथ इंटरेक्शन है, तो वी वांट टू मॉडल इट, सो व्हाई डोंट वी गो फॉर एन एग्जैक्टली प्रिडिक्टेबल मॉडल विद एज मेनी कॉम्प्लिकेशन एज पॉसिबल? नहीं, अलजेब्राइकली मैथमेटिकली कर तो सकते हैं, बट व्हाई डू वी वांट सिंपल system when we have computers to solve even complicated systems? Basically पैटर्न बनाने की कोशिश क्यों कर रहे होते हैं? नहीं, जनरलाइज तो आपने करना है, वो तो फिर जितने ज्यादा पैरामीटर होंगे उतना ज्यादा जनरल होगा। हाँ। जी। हम्म। नहीं, असल में मैं इनका सुनूं फिर मैं बताता हूँ जी, आप हाँ। सो ये दोनों तीनों बातें ऑलमोस्ट सिमिलर हैं, तो अब मैं इसको ना यूं देखता हूँ। अब देखिए, हमें ऑलमोस्ट सारी फिजिक्स का पता है, फिजिक्स का मतलब है वी नो द बेसिक लॉज, so we can build computer models very easily that can take into account lot of variables and whenever we have to do something, we just put the parameters and variable, it will just churn out some numbers and we can just use them. So why, let's say, spend 2 years on learning quantum mechanics when I can just put the equations into a computer and specify initial condition. I can get the dynamics, assuming computer is working okay. And the answer is this, कि उससे आपका problem तो solve हो जाएगा, but you won't be able to let's say develop ways of solving different problems or inventing or learning different physics or trying to predict something even without doing computation. I mean, Feynman के काफी famous quote है कि understanding का मतलब ये है कि when you can sort of approximately predict what will happen without computing. और वो जो चीज उस वक्त आती है when you learn to model things simply. और जब एक चीज को आप मॉडल करें तो सबसे पहले आइडेंटिफाई करें what is more important और what is critical. फॉर एग्जाम्पल, अगर आप इस पेंडुलम को देखें एयर के अंदर, आई कैन से ओके अगर डेंसिटी वेरिएशन है, इट्स नॉट बिग थिंग, जी वेरिएशन इज नॉट बिग थिंग, दिस इज ऑलमोस्ट स्ट्रेट, so this is minimal, so I can forget everything, just imagine I don't even have to model air as individual particles. It will just include lot of equation. I can just think of it as a ball moving in a fluid, and I have simple relations of a ball moving in a fluid, उसकी velocity और fluid की जो drag है उससे compare करके I can just model it very easily. और उससे जो आपका एक तो variable कम है, at the end what you will have is something elegant and simple, though it will not be fully accurate. It may not work everywhere. हो सकता है आप इसको उठा के उधर ले जाएं नॉर्थ पोल पे, तो वहां पे टेम्परेचर इतना कम है कि यू माइट नॉट हैव और मे बी हवा इतनी तेज चल रही है कि योर मॉडल फेल्स. सो देयर माइट बी एक्सट्रीम कंडीशन जहां पे आपका मॉडल फेल हो जाए, बट इन मोस्ट सिचुएशन जब आप वो इक्वेशन कर लेंगे, सो लेट्स से यू गेट समथिंग दैट इज प्रोपोर्शनल टू the some parameter, so then you don't even have to do many calculation. You can sort of start developing intuitive pictures. Okay, so असल में सारी डिस्कशन का जो मकसद है वो ये है कि we are going to be discussing open quantum system, and we will see that there are many ways of, first of all, modeling the interaction of the quantum system with the environment, but we have to make usually a decision when we are modeling a realistic situation कि what is more important, because जितने हम parameters ज़्यादा कर लेंगे उतनी we will develop a formalism that can take it to everything, but it will soon get out of hand. So we have to be, every time we model an open quantum system, we have to ask ourselves, is the model over specified? What are the important things? Just keep that, so that at the end you get some simpler result that you can use to get some intuition. Okay, so just for the sake of concreteness going on, जो symbols जो मैं अभी use करूंगा, I'm going to use symbol P for the principal system, not for pendulum, and then environment as E, and then this whole total system as S. So I will reserve S for the universe, P for the part of the universe that I'm looking at, or the principal system that I want to work with, and then this E is whatever is in the universe except this principal system. Okay, so generally we can think about the interaction of the principal system with the environment in three ways. So interaction can be strong, it can be weak, or it can be somewhere intermediate, or we can also think about like this. So this might be an interactions which might be happening continuously. For example, अगर ये आपका हाइड्रोजन एटम है, ठीक है, ये जो आपका प्रिंसिपल सिस्टम है, and it is placed at a temperature T. There might not be any, physical thing over here, but if this environment is maintaining a temperature T, it means there is a background radiation spectrum which is interacting with your hydrogen atom. So depending on the, the value of temperature, this interaction might be weak or strong. And this might be, continuously happening. You want to understand what's going to happen with the hydrogen atom over a long period of time. But then there is actually another type of interaction, which is the norm in quantum computers mostly, which is that we have a closed system. Then we sort of open a window, we do something, we start interaction with an open system, and then we close it again. So it's something like this. For example, I have a qubit. Okay, so it's a two-level system. It might be, a spin-half particle or something in a magnetic field. And then suppose there's nothing in the universe. So it means if there's nothing in the universe, this is a closed system, right? But let's say in the from the universe comes some pulse of frequency such that, this frequency might be equal to this energy gap. And this pulse might come for, some time delta t, and then the pulse is gone. So we had a closed system. Then this closed system interacted with the environment, and then the system was made closed again. So this type of thing is extremely common in quantum computers, because that's how quantum computers work. We have a bunch of qubits. We want to do, let's say, X gate on this one and Y gate on this one. So we send some pulse here and some pulse here with some different parameters. So something happens to this, something happens to this qubit, and then the pulses are removed. So we can also have an interaction of the principal system with the environment like this, that the system might start as a closed, then open, then closed. Or it might be something like the more realistic actually could be situation like this, that if I draw the strength plot, so when the system is closed, there might be some noise coming in. So the system is weakly coupled to the environment, then it is strongly coupled, and then it's weakly coupled to the environment again as time goes on. So we have, either continuous coupling, and that continuous coupling can be weak or strong, and we can have the interchange of weak and strong coupling as a function of time. Open system. हाँ, okay, जब हम गेट अप्लाई कर रहे हैं, बेसिकली वी आर सेंडिंग सम पल्स. फॉर एग्जांपल, अगर आपका सिस्टम इस लेवल पे है, इफ आई वांट टू टेक इट टू द अपर लेवल, आई नीड टू सेंड अ फोटॉन सो दैट इट अब्सॉर्ब दिस फोटॉन एंड गोस टू द सिस्टम 1. So that's X gate. So if जो quantum gate है, that is basically interaction of the qubit, which is assumed to be closed with environment in a controlled way, so that something controlled happen to the system, and then the system is closed again. हाँ. मैं कह रहा हूँ कि अगर उसको बिल्कुल क्लोज नहीं, तो we can assume like this, that the system is first initially weakly coupled, then it is strongly coupled, and then weakly coupled again. अगर coupling strength का plot करें, so it can be like this. So जो closed system की approximation है, we will be using it again and again, because it's not something which is wildly different from what we want to do, because sometime our system might not be interacting very strongly with anything. So during that phase, we can almost approximately imagine it as a closed system. हम्म मतलब कि ये जो क्वांटम कंप्यूटर है, इट्स बंच ऑफ क्यूबिट्स, ठीक है. सो ईच क्यूबिट इज अ प्रिंसिपल सिस्टम, एंड देन एवरीथिंग इस क्यूबिट के लिए ये प्रिंसिपल है और बाकी सारी क्यूबिट इसके लिए इन्वायरमेंट है. इस क्यूबिट के लिए यू कैन थिंक ऑफ दिस एज अ प्रिंसिपल सिस्टम एंड एवरीथिंग एल्स एज एनवायरनमेंट, या वी कैन थिंक ऑफ ऑल थ्री एज अ प्रिंसिपल सिस्टम एंड एवरीथिंग एल्स एज एनवायरनमेंट एंड सो ऑन. ठीक है. Okay, when we have to do gate, essentially we send a pulse that does something to this qubit, so that's a gate. So that is equivalent to, there are two ways actually of thinking this operation. One is that we can continue to think of this as still a closed system with a unitary operation, because we can perform unitary operations on a closed system, or we can think of it as a principal system acting with an environment through some interaction. Okay, so hopefully as we move on, it will become clearer. Okay, so अब ये जो सिस्टम की इंटरेक्शंस हैं या एवोल्यूशन है इन जनरल, अब देखें यहाँ पे दो तरह के हमारे पास सिनारियोस हैं. एक तो ये कि अगर हम अपने क्लोज सिस्टम को देखें तो उसकी एवोल्यूशन को भी यू ऑलरेडी नो दैट क्लोज सिस्टम evolution can be represented by unitary operation, right? और जो अगर आप प्योर स्टेट्स में है, so you can use the bracket formalism. For example, the state after some unitary operation u can be written like this. Or if our closed system is in some mixed state, then we can also do it using density matrices. But this operator in both cases is unitary operator. That's how the closed systems evolve. They evolve unitarily. But the open systems, we can expect that in general they may not evolve unitarily, and the mathematical formalism that is used to address the evolution of open systems, it's called quantum operations. And there are many ways of specifying these quantum operations. So the interaction of this principal system with the environment, we can express it actually in a couple of ways, and that's what we are initially going to learn about. And this operations, this is also sometime is referred to as actually most of the time as a quantum channel or just a channel. It comes from the language of communication theory. So but it doesn't necessarily have to be like a physical channel. You can think of it like this. For example, अगर आपके पास एक memory है, उसके ऊपर उसमें कोई qubit stored है, and let's say you start keeping track of this at time t is equal to 0, and the qubit is still here, or after for some time, let's say delta t, either it's just there and you're just trying to think of what noise is doing to this, or maybe you are writing a reading of some things from this. All of these interactions, this is called a quantum channel. Whatever happened to this qubit is called a quantum channel. For example, अगर इसकी state जो है वो time t is equal to 0 पे raw है, तो इसकी जो state है after time let's say delta t, this is suppose given by some e of rho. It's a function of the state at t is equal to 0, and whatever this function is, we call it a channel. Because equivalently you can think of it like this, because that I have some optical fiber, and I put a photon in here in one of the two polarization state or a linear combination of those polarization state, and the photon passes through this channel. And while the photon goes from here to there, something happens to it along the way. So then the state of the photon here is rho, and the state of the photon here is E of rho. So you can think of this evolution either happening, in space or in time. So we are going to use the word channel for everything that happens to a quantum system. But it doesn't mean that we are always thinking about the state passing through a physical, channel and going somewhere else. The state might be just staying right there. ठीक है, ये terminology थोड़ी सी जो confusing है शुरू में, I want to clear it out. And whatever happens to our quantum system during a certain time, we might not actually be referring to time explicitly all the time. We might be talking in terms of discrete set of operations happening in a sequence. So time might be implicit, because we are talking about order के पहले ये हुआ, फिर ये हुआ, फिर ये हुआ. So उसमें time जो है वो explicit हो भी सकता है और नहीं भी हो सकता. So all of this is in general called quantum operations, whatever happened to a quantum system, and we represent it using a quantum channel or a quantum map, or just a function or a map, or there are a couple of other names out there as well. Okay, so just to give you an example, for closed system, the map is just this. Okay, so, and for open system, this map would be more general than just this unitary evolution. And to specify this map, whatever operations we specify, we call them quantum operations. And there are basically two ways that we can do it. Two ways to specify quantum operations. Let me first specify the one that I will discuss a couple of lectures down the road, and then the next that we will discuss today. So this is a method which is based on the system environment interaction, in which we model usually environment much more explicitly and in much more detail. And we know much more about the physics and interaction that is going on between system and the environment. And we essentially come up usually with differential equations. These differential equations are called master equations that specify the behavior of the system given a particular interaction of the system with the environment. So we will study this technique as well. So in this, we our focus is usually on understanding what is going on between system and environment in more detail. For example, कि अगर ये एक spin chain है and there are spins all around it and at a certain temperature with certain properties and so on, what happens to this? So there's more explicit sort of physics of system environment interaction that is modeled by this. And we can also discuss continuous evolution, since we have master equations which are differential equations in time. So usually for continuous evolution, this approach is very suitable. And for explicit interactions. So एक्सेल में जो अदम है उनका काफी सारा जो काम है वो इस एरिया में आता है. But in this course, I am actually going to focus more on another equivalent formalism, which is the operator sum method. And in this method, we start with this system environment interactions, but usually we abstract the environment away because here our interest is more on the principal system and what's going on with it and how it is evolving. And usually in a discrete fashion, but also the continuous evolution can also be discussed with this. So with this operator sum method, we will initially start from system environment, but later we will see that we can come the reverse way from some axioms as well. This is axiomatic as well. So from few axioms, we can come to this method. So this method is more suitable if we want to, for example, understand the noisy evolution of quantum systems, especially in quantum computer setting, where we have digitized our operations. So we are sending pulses here, there. So everything is happening in discrete steps. All right. So did you? फर्क खैर ज्यादा डिटेल तो जब करेंगे तो पता चलेगा. फिलहाल आप यूं समझ लें कि ये अप्रोच है जिसमें we model system and environment more explicitly. ठीक है. Or we start essentially from Schrodinger equation, and from that we can get differential equations that govern the behavior of system under a specified environment. ठीक है. So differential equation को solve करें, you can understand the properties of the system. The second approach is, again, we are still interested in understanding the impact of environment and noise and system, but here we usually abstract this environment away. And so this is more abstract and this is more physical. Okay? Because this keeps the environment sort of in more detail and up towards sort of the final solution. Here we usually abstract the environment away quickly, and we say, okay, for example, a qubit here. We want to perform X gate or Z gate and so on. Okay, and we know that there is environment which is creating noise here. बाज़ का environment अपनी तरफ से कोई X gate लगा देता है या rotation gate पे लगा देता है कुछ भी. So we will develop a way that we can come up with an operator sum method so that we can model the environment. And then once we have modeled the environment, after that we have just some operators for this principal system only, and we forget about the environment. So this is a way in which we abstract the environment away at the initial stage. So environment is there, but it is in the operators that we developed to model the environment. But soon after that, we just forget about the environment. We're just working with the system. Okay. So let me start with this operator sum method. And actually, we can easily see it from this picture. If we have a closed system, we can think of it like this. We have the state of our system. The state might be mixed state, pure state, whatever. And we have a unitary operator acting on this state, and we get our map. So this E is a map from the input state to the output state. And if the system is closed, the evolution is unitary. But if we have our system and we also have environment, so by the axioms of quantum physics, and when we combine both of them, this becomes our system now. So this whole is evolving under a unitary evolution, because that's the axiom of quantum physics. The closed system has to evolve under unitary evolution. And if we just look at our subsystem, at our system, now there's some map or some channel which is connecting the input state of the system to the output state. And let's say we are not focusing what is happening to the environment. This does not necessarily have to be a unitary evolution. There's nothing in quantum physics that says this. So both of these tools are essentially a way of trying to understand given the environment, because this U will specify the interaction of the system and the environment. But given this, what is the map that just connects my this row to the output? And this in general is not a unitary evolution. And now question is how to develop a formalism or a representation for this thing. We can do it very easily using the density matrix formalism that we have already have. कैसे? ये जो E है, हमें पता है कि अगर ये मेरा सिस्टम है, ये environment है, तो इनकी joint state क्या होगी? ये होगी. और under unitary evolution ये क्या होगा? U dagger and U. क्योंकि मुझे अब ये तो पता है कि सिस्टम तो मेरा यूनिटैरिली इवॉल्व नहीं कर रहा, लेकिन सिस्टम इन्वायरमेंट जॉइंटली तो अभी भी यूनिटैरिली कर रहे हैं. और अब ये मेरे पास टोटल स्टेट आ गया, ये जो जॉइंट स्टेट है ना इन्वायरमेंट और सिस्टम की. अब इसमें से अगर मैंने सिर्फ सिस्टम की स्टेट निकालनी है तो उसके लिए क्या करना पड़ेगा जी? पार्शियल ट्रेस. यू जस्ट ट्रेस आउट द environment, and this is the general form actually. And if you want to see what is happening in the environment, you can also do that very easily. कि अगर आप इसको सिस्टम को ट्रेस आउट कर लें, you will see what is happening to the system environment. So जो हम लेबलिंग करते हैं ना सिस्टम environment, this is to some extent just an arbitrary labeling, because the same tools that we can use to study what is environment doing to the system can also be used to study what the system is doing to the environment. But since in practical situations environment is usually too big and too complicated, that we are not interested in that, and we are usually interested in a very small part of the universe, just a few qubits, few atoms, and few things like this. All right, so this is the foundation actually for both methods. Here we will be using it in a more general fashion and developing differential equation, but here we will try to specialize it so that we can use it easily for understanding noisy quantum computers. Didi? Huh? It's possible. नहीं, इंटरेक्शन तो है, लेकिन हम तो बस ये देख रहे हैं कि उस इंटरेक्शन की वजह से अगर मैं जस्ट सिस्टम को देख रहा हूं तो उसको क्या हो रहा है. ठीक है. और ट्रूली स्पीकिंग जो सिस्टम को मसला होता है इंटेंगल से है, इंटेंगलमेंट. अगर आपका जो भी यूनिटरी ऑपरेशन है वो आपके सिस्टम और आपके एनवायरनमेंट को इंटेंगल नहीं करता, तो देन एसेंशियली सिस्टम इज नॉट डूइंग एनीथिंग टू योर सिस्टम, एंड सॉरी एनवायरनमेंट इज नॉट डूइंग एनीथिंग टू योर सिस्टम. क्यों? क्योंकि इसका मतलब है कि अगर आप ये जो सारा है इसको एट द एंड अगर यूं लिख सकते हैं, रो प्राइम टेंसर रो इन्वायरमेंट. अब इसको अगर मैं इन्वायरमेंट में ट्रेस करूंगा तो this will simply be giving me one, and I'll be having this one. So it means my system is only unitarily evolving. Okay. जी. हाँ. So that's where your ingenuity as physicist comes in. Environment usually has a lot of degrees of freedoms. You have to understand which of those degrees of freedom are important, really, which are impacting your system. And we will be studying as well. For example, if we have a two-dimensional system, a single qubit, how many maximally a general environment कितने dimensional का जो है वो उसको impact कर सकता है. कि अगर environment की हम, क्योंकि environment को भी हम Hilbert space में करेंगे ना, तो ज्यादा complicated environment का मतलब है ज्यादा बड़ी Hilbert space. But if your own system is, let's say, a d-dimensional system, there's a limit that how big environment you need to have to be able to understand general interactions. लेकिन हम usually जो काम करते हैं उससे भी बहुत कम पे करते हैं. वी जस्ट ट्राई टू सी कि एनवायरनमेंट का मेजर इम्पैक्ट क्या है, ठीक है, एंड और दैट्स हाउ वी एक्चुअली सॉर्ट ऑफ वर्क विद। बल्कि जो ये दोनों अप्रोचेस है ना, ये सॉर्ट ऑफ इससे को कॉम्प्लीमेंट करती हैं। ये जो डिफरेंशियल इक्वेशन बेस्ड अप्रोच है, यूजुअली दिस इन्फॉर्म्स दिस मेथड, क्योंकि इसमें हम ज्यादा एक्सप्लिसिटली देख रहे होते हैं कि हमारे गिवन सिस्टम के लिए गिवन इन्वायरमेंट में इंटरेक्शन कौन कौन से जो टर्म्स है वो ज्यादा स्ट्रॉन्ग है। And then when we are using this operator sum method, agarche we can again model the environment again very generally, but we can only keep the operators corresponding to those terms that are, you know, strongly impacting our system, and we can just forget about the rest. Okay, so again अच्छा इसमें एक सबसे बड़ा सवाल तो भी रहता है कि यू को कैसे स्पेसिफाई करें। आप अपने सिस्टम को कुछ कर रहे हैं, लेकिन ओवरऑल हो तो आपके सिस्टम और इन्वायरमेंट दोनों को कुछ रहा है, लेकिन आपका इन्वायरमेंट यूजुअली अननोन है, तो यू भी अननोन है। सो हाँ, हाँ, तो उसका जवाब यही है कि अगर तो आप बैठ जाएंगे कि इसको एग्जैक्टली मॉडल करना है, देन यू आर लॉस्ट। व्हाट यू हैव टू थिंक अबाउट के कौन सी इंपॉर्टेंट चीजें हैं जो कि इन्वायरमेंट से उधर इम्पैक्ट कर रही हैं। सो दैट्स वेयर एक्चुअली योर रिसर्च एंड एवरीथिंग कम्स इन। हाँ, बिल्कुल। Okay, let me give you an example. I think this will help make things clear. Suppose I have a single qubit in some state rho, and I have my environment in a pure state. And suppose the unitary operation is this control NOT gate between the principal system and the environment. And let's find out what this map is. देखिए बहुत आइडियल किस्म का लिया है। इन्वायरमेंट जो है वो भी मैंने प्योर स्टेट में स्टार्ट करा है, और ये असल में यूजुअली यू विल सी, मैं जैसे एक कमेंट अभी से कर दूं कि हम इन्वायरमेंट को वी विल बी थिंकिंग ऑफ इट स्टार्टिंग इन अ प्योर स्टेट, इन सम प्योर स्टेट। अगरचे यू नो ये इतनी अच्छी assumption तो नहीं है, क्योंकि इन्वायरमेंट इज बाय डेफिनेशन इज समथिंग वेरी नॉइजी, सो इट माइट बी इन अ वेरी कॉम्प्लिकेटेड मिक्स स्टेट। लेकिन वी ऑलरेडी हैव द प्यूरिफिकेशन थ्योरम कि अगर कोई भी आपके पास सिस्टम है वो मिक्स स्टेट में है, वी कैन ऑलवेज कॉम्प्लीमेंट इट विद अनदर रेफरेंस सिस्टम, एंड देन सो दैट both of them are jointly in a pure state, right? So this assumption is not something which is far from reality. And since environment by usually it's very big, complementing with something you know else as well, it doesn't going to do us anything very bad. So we will usually be assuming our environment to be starting in some pure state. Okay, so let's try to work out this map. So in this case my u is this. Everybody understands कि ये जो मैं लिख रहा हूँ why it's true? कि लेफ्ट साइड पे कंट्रोल बिट है और राइट साइड पे टारगेट बिट है, ठीक है। सबसे एंड पे कौन आए थे, क्या नाम है आपका? जैन, ठीक है। जैन आपकी क्लास तो नहीं होती इस वक्त? तो सेमिनार तो खत्म हुआ था, हमने बाद में फिर शुरू किया था जी। अच्छा 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 अच्छा, चले तो कैन यू अंडरस्टैंड के व्हाई दिस यू इज अ रिप्रेजेंटेटिव ऑफ अ कंट्रोल नॉट गेट? ओके, सो चले किसी और से, अब्दुल्ला आपको तो पता है इस चीज का। ओके, कोई और बंदा जैन के अलावा जो समझता है कि इट डजंट अंडरस्टैंड व्हाई द यूनिटरी ऑपरेटर करस्पॉन्डिंग टू कंट्रोल एक्स गेट इज दिस? अफसा जी, समझते हैं ये ठीक है? हाँ, बिकॉज कि अगर ये 0 0 पे एक्ट कर रहा है तो 0 0, अगर ये 0 1 पे कर रहा है तो 0 1, अगर ये 1 0 पे कर रहा है तो 1 1, अगर ये 1 1 पे कर रहा है तो 1 0. So this is unitary operator. So I can find the joint row So this is now the density matrix corresponding to environment. So environment का जो density matrix है मैं वो यहाँ से लिख सकता हूँ like this. So this is environment. This is the arbitrary input for this one. So let's now apply U here and U dagger here. Trace बाद में लेते हैं. So this is the, you know, system environment joint state. Okay, so ये U है, raw tensor. ये जो U dagger है, इसके लिए इस पे dagger implement करना है. इस पे dagger होगा तो यही आ जाएगा. Dagger आपको पता है ट्रांसपोज होता है और कॉन्जुगेट होता है, तो ये सारे तो रियल हैं, तो ओनली ट्रांसपोज हैज टू बी टेकन. सो इसका ट्रांसपोज लेंगे 1 0 इधर आ जाएगा, 1 1 उधर चला जाएगा. इसका लेंगे तो ये आ जाएगा 1 1 1 0. लेट्स वर्क आउट इसका इंटरेक्शन इसके साथ. अब ये जो लिखा हुआ है ना 0 0 0 0, इसका असल मतलब तो ये है, ये पहला 0 इसका और इसकी पहली स्टेट 0 टेंसर 0 0, राइट. और इसी तरह इसका मतलब है 0 0 टेंसर 1 1, इसका मतलब है 1 0 टेंसर 0 1 एंड सो ऑन. तो ये मैं इसलिए अब एक्सप्लिसिटली लिख रहा हूं कि जब इसको इस पे ऑपरेट करना है तो दिस विल बी ऑपरेटिंग विद दिस थिंग एंड दिस विल बी ऑपरेटिंग विद दिस थिंग. अब जब ये पहली टर्म इसके साथ होगी तो आई विल गेट रो टेंसर 0 0, ये वाला नहीं, सॉरी ये टेंसर नहीं आएगा, टेंसर. अब ये 0 0 जब इस 0 0 से होगा तो क्या होगा, वी विल गेट 0 0, क्योंकि दिस 0 into 0 is 1, so ये 0 और ये 0 आ जाएंगे, प्लस रो into 0 0 टेंसर. ये जो 0 0 है ये है 1 और ये है 1, तो ये 0 मिल जाएगा, राइट. ठीक है जिशान, आपका नाम क्या है? उमर. क्यों उमर, इज दिस ओके कि यहाँ पे 0 आना चाहिए? ओके. अब इसी तरह ये 0 1 है, ये 0 है और ये 1 है. जब इसके साथ होगा तो 0 into 0 is 1. ओके, सो ये आ जाएगा रो into 1 1, रो 1 1 टेंसर 0 0 into 0 1 will give me 0 0 1 हो गया, तो ये 0 और ये 1 0 1 प्लस ये आखिरी वाले के साथ 0 ही आ जाएगा, क्योंकि ये 0 0 जब ये 1 0 1 1 से होगा तो 0 होगा. सो ये आ गया. तो ये दो टर्म है, एक ये है और एक ये है. इसी तरह ये u यहां पे लिखें, ठीक है, एंड यू वर्क इट आउट. सो लेट मी जस्ट सी इफ आई हैव रिटन द आंसर और नॉट. यस. सो आपको मिल जाएगा जो जॉइंट स्टेट है सिस्टम इन्वायरमेंट की, वो होगी 0 0 रो 0 0 टेंसर 0 0 प्लस 1 1 रो 1 1 tensor 1 1. And by the way, this is usually we represent with P naught. ये प्रोजेक्टर ऑपरेटर है, so this is P1. Let's call it this P1. इसको मैं लिख सकता हूँ P naught रो P naught. इसको भी लिख सकता हूँ, but let's keep it as it is. P1 रो P1 tensor 1 1. अब जो है हम environment को trace out कर देते हैं. So the map for the qubit for this is, so this is single qubit, this is single qubit. Map of the principal system is tracing over environment of this thing. तो इसका trace लेंगे तो हमने इसका और इसका trace find करना. तो ये 0 0 है, ये 1 हो जाएगा, और ये 1 1 है, ये भी 1 हो जाएगा. So we will get P naught row P naught plus P1 row P1. So this is the map for this qubit state. Let me explain it a little bit कि ये हो क्या रहा है. बेसिकली अब आपसे अगर कहा जाए कि एक आपके पास सिंगल क्यूबिट है, वो किसी स्टेट रो से शुरू होती है, और कोई एक इन्वायरमेंट है जिससे वो लेट्स से इस तरह से इंटरेक्ट कर रही है, तो देन ये किस तरह से स्टेट इवॉल्व होगी. सो you can forget about this thing, whatever is here, and just if you focus on this thing, now you can use this thing to simply understand the input output relation for this single qubit without worrying about the environment. क्यों? क्योंकि environment का जो impact है वो इनके computation में आ गया है. And this is actually the operator sum method. कि हमने जो अपनी स्टेट है उसको दो टर्म्स के सम के फॉर्म में लिखा है, एंड ईच टर्म इज बीइंग एक्टेड ऑन बाय एन ऑपरेटर फ्रॉम दिस साइड एंड दैट साइड. इन जनरल एक्चुअली बाद में हम देखेंगे कि राइट साइड वाले ऑपरेटर यूजुअली इस साइड वाले ऑपरेटर का डैगर होता है. क्यों? क्योंकि जब ये यू है और ये यू का डैगर लेंगे ना, तो इसका जब ये पार्ट्स बनाते हैं तो जो ऑपरेटर इसके साथ आ रहा है ना वो डैगर वाले ऑपरेटर होते हैं. बट क्योंकि ये सारा चीज रियल थी और इसलिए और ये पी नॉट जो है ये अगर आप मैट्रिक्स फॉर्म में लिखें तो 1 0 0 है, और P1 जो है मैट्रिक्स फॉर्म में 0 0 1 है. सो दैट्स व्हाई, बल्कि P1 और P डैगर एक दूसरे के बराबर ही होते हैं. Anyway, so this is the operator sum representation. These operators are called cross operator, K or OUS. अच्छा, लेकिन ये देखें कि ये स्पेसिफिक एक इन्वायरमेंट हमने चूज किया, ये कर क्या रहा भला? इट्स जस्ट मेजरिंग योर क्यूबिट, क्योंकि ये दोनों वो मेजरमेंट ऑपरेटर्स हैं. और अगर आपको याद हो तो हमने जब मेजरमेंट को पढ़ रहे थे तो हमने कहा था कि यू मेजर योर स्टेट रो and you forget the measurement results, then this is the state of your output after that. It's just the sum of all possible post measurement states. Anyway, this is just one particular example. Any other question? If not, let's keep going. So in general, अब अगर मैं बात करूं about operator sum representation की, जी usually we know this thing. हाँ, सिस्टम वी अज्यूम के सिस्टम उसी को कह रहे होते हैं जिसके बारे में सब कुछ पता है. हाँ हाँ जी जी. Okay, so in general, let's say we now have a multi-qubit system in state row, and we have some a multi-qubit environment in pure state E0, and then some U is acting on it. Let's see what's the map in general in terms of sum of operators. Imagine that EK is a basis set for environment. Okay, so for starting, let's assume that we know everything about the environment as well, and that its Hilbert space has this basis EK, and suppose our environment starts in one of those states. So if this is, and in whatever those state it starts, we call it E naught. So let's work out the map that connects the input of the state to the output of the state, which we have already seen as the trace over this thing. Now I can put the identity operator here because of the completeness relation. U row tensor E naught tensor U tensor. ठीक है? I assume that this is a complete basis. So यहाँ पे identity put कर दे, identity की जगह पे मैंने ये put कर दिया. अब ये चूंकि trace जो है वो linear operator है, this trace can go inside this sum, और जब inside आता है, so we have you know this bra, this cat and this bra, all of this. So you can imagine it like this, for example, right? So this U operating here, this is operating here, everything, you know, operating here. So this is sort of some a state that has all of this. Then the trace we already know is just to recall, okay? अगर आपने trace find करना हो ना इसका, so this is phi psi, phi inner product psi. So using this thing, I can now write this map as sum over k ek u row tensor e naught u dagger ek. Okay, and then after this, I can imagine that this unitary operator, you know, is a sum of terms acting on the system and acting on the environment. So you can think of this U as containing terms like this, where this, you know, sum over PE. So because this is a operator which is acting on the joint system environment state, so it means it can be written as, you know, sum of the products of operators on system and the environment. So it has this form. So if I assume this, then I can write it like this, that this has some part acting on here and some part acting on this, and the part that is acting on this one, I can, you know, bring it with this thing. So this would become ek u e naught and then rho, and similarly the part of this operator that is acting on the environment can be sandwiched between E naught, U dagger, and EK, and the part of this operator which is just on the environment, this will simply get out of this inner product when we actually perform this inner product. So this is a new operator, let's call it EK rho, and this is a new operator which is just the dagger of this thing. So this is the in general operator sum representation where EK is EK U E naught. And just to see from here, जब आप ये inner product find कर रहे होंगे operator का, तो only जिसका environment वाला part है वो इनके दरमियान में sandwiched होगा. जो ये UP वाला part है, this would be out. So just do like this. So अगर आप sum लिखें, this would be UP tensor EK UE E naught. So this is the general operator sum representation for this quantum channel. So just to rephrase, जब हम सिर्फ सिस्टम को देख रहे हैं, we call it channel, which essentially means the operations that are being performed on our principal system by the environment. And there are like sort of two equivalent representation. The one is the differential equation representation. We'll talk about it later on. But the one that we are going to focus in this course mostly is this operator sum representation, where we think about the state row being acted upon by two operators. And these operators are given by this. And we can easily see that because of the completeness of EK, I can quickly verify one other result, that if we require, and we will usually do, except at a couple of places that I will talk about, that the trace of the output of system is 1. If we require this, then we can see that trace of sum over k ek row ek dagger is 1, which means that I can write it trace k, आप इसको साइक्लिकली ना चेंज कर सकते हैं, इसको इधर ले हैं, सो ई के डैगर ई के रो इज इक्वल टू 1, जो कि ट्रेस है, ट्रेस के अंदर आप इंटरचेंज कर सकते हैं. अब फॉर आर्बिट्रेरी रो, इफ वी वांट दिस थिंग टू होल्ड, देन दिस मस्ट बी एन आइडेंटिटी. सो इसका मतलब है कि जो हमारे ऑपरेटर्स हैं वो ये कंडीशन इनको सेटिस्फाई करनी चाहिए. अब देखें, अब अगर आप जो ओपन क्वांटम सिस्टम है उनके एक्सियम्स की बात करें, उनके रूल्स की बात करें, लेट मी जस्ट कंपेयर क्विकली जो क्लोज सिस्टम है और जो ओपन सिस्टम है. ओपन सिस्टम मीन दैट आई हैव अ सिस्टम व्हिच इज acting with environment, but I'm not looking at it, and just I'm looking at my system. क्योंकि अगर मैं environment को भी शामिल कर लूं, then this is the same as closed. So for closed system, we had rho, which represents the state of the system, density operator, with the condition that trace rho is 1. And then our evolutions were given by unitary operators, and our, which means that u dagger is identity, by the way, and we have measurements operators such that mk dagger, its trace is the probability of getting this thing. Now, how does this translate to open system? Again, in open quantum system, we have density matrix, which represents the state of the system. And again, our trace is 1 for these states, except when we do measurement, okay? Because then the state collapses. But the major difference is now in evolution. Now evolution is given by this thing, ek row, ek dagger. So ये और यहाँ पे जो map है, it's given by this unitary map. So instead of unitary map, now we have a general map, and these operators, they are not unitary operators, okay? They satisfy this completeness relation, which of course, अगर आपका K1 है, सिर्फ एक ही operator है, तो this reduces to the unitarity requirement. क्योंकि अगर सिर्फ एक ही operator है set के अंदर, तो then even dagger had to be identity. And then for measurements, we have the same thing. अच्छा, अब यहाँ पे ना कुछ लोग measurement को भी इसी के अंदर include कर लेते हैं, क्योंकि ये देखें इसकी शक्ल और measurement वाले की शक्ल ना वो मिल जाती है. But then they say, okay, the trace can be between 0 and 1, so non-trace preserving. But what we will be doing in this course, we will be keeping measurements separate from this evolution, and then we will be requiring all of our channels to be trace preserving, because measurement is also a channel. It does some quantum operations, but that channel doesn't preserve trace. So we will be concerned with trace preserving channels only in this course. पीस वाइज नहीं, फिर नहीं जो इंडिपेंडेंट है वो यूनिटरी नहीं है, दे डोंट प्रोडक्ट टू आइडेंटिटी. Okay. All right, so let's do a quick problem. Suppose that we have a system environment interaction. Suppose we have a single qubit system and our environment starts in a state 0, and this is also a single qubit, this is also a single qubit. And suppose that this has a basis state as 0, 1. You have to find this map if this U is specified like this. These are projector operator, this is identity, this is X operator. So जो E है ये find करें. In other words, find me E0 and E1. क्योंकि इसमें दो ऑपरेटर होंगे ना, ऑपरेटर सामने. ये ले लेते हैं, एक ले लें बाकी. इसमें बस ये चीज आपने अपने ध्यान में रखनी है जो मैं यहाँ पे बात कर रहा था. You can start with this basis and environment is in 0 basis. तो जब ये sandwich करके ये निकालना है ना, तो this inner product is only going to be applied to the environment part of the operator and nothing should happen to the principal system part of the operator. Let me close the